Hello guys, welcome back to my channel Gamma Die Gamma. And let me first say it's a fine day for YouTubing. So welcome back again. I hope you watched the last video, which was pretty much in demand, if not more in demand than the Stokes theorem video. So please check that out if you haven't already. In this video I thought to myself, we could start a new topic. And not really a new concept, but application of something we learned before. To be precise, application of the Einstein subscript summation convention to prove some identities from vector algebra. And towards the end, I might actually give you some insights into what the vector gradient looks like, and I'm going to have to introduce, at least for this video, the idea of a rank 2 tensor. Okay, so we have a lot planned ahead. Let's get started. Okay, so the first identity or property I want to show you is actually called the scalar triple product. So what is this? Assuming you have three vectors A, B and C, and you have them in this construct, A dotted with B cross C. Okay, what do we do with this? Let's use our beloved subscript summation convention. Notice I'm using different indices for the different vectors because they're clearly independent here. Okay, so we have AI, EI hat, dotted with, well, BJ, CK, Levi-Civita, JKL, EL hat. And now pull the scalar components outside along with the Levi-Civita, and the EI hat dotted with the EL hat gives you a Kronecker delta IL. I'm showing you a little more steps for this case. In the future we might skip many steps. Okay, with this Levi-Civita, with this Kronecker delta I mean, we can change the L to an I, and notice we have a Levi-Civita JKI, which we can write as IJK using the property of permutation of the Levi-Civita symbol. Okay, and notice this thing, if we kind of reverse steps a bit, you notice a kind of pattern. This kind of looks like, say, AI, E sub I, crossed with BJ, E sub J, dotted with some, I don't know, CM, E sub M. And it makes sense because if you do everything, which was precisely this guy. So we can write A dotted with B cross C as, well, this guy here, which is A crossed with B dotted with C. And another interesting thing we can do is we can take another permutation of this. So KLJ, we can take KLJ or KIJ. Yeah, there's no L, my bad. KLJ, and we still have a positive sign because it's a even permutation. And with this, you notice this is nothing but B dotted with C cross A. And again, you can do this reverse engineering process, and you'll see one way of seeing it is, notice the last index of the Levi-Civita has to match the vector that will be outside the cross product, that will be dotted outside. So that's one way of looking at it. So you see the scalar triple product has this definitive structure: A dotted with B cross C is equal to C dotted with A cross B, which is equal to B dotted with C cross A. So you notice we get these things because of the permutation relationship of the Levi-Civita symbols, which are a result of the structure of the cross product. And you see ABC are obey this certain cyclical order here. So ABC, they're going this way. CAB, they're still going in the direction of the arrows. BCA, still going in the direction of the arrows, because if we were to reverse the direction, we would have a negative here. So this is like an extension, this is like a vector extension of the Levi-Civita symbol. For the Levi-Civita, we saw whether the indices were in this were in a certain cyclical order. Here we're seeing whether the vectors are in that order. And again, as you might suspect, if two vectors are equal, then the scalar triple product is 0. Again, which is, kind of makes sense if you connect it back to the Levi-Civita symbol, because two indices that were the same resulted in a 0 Levi-Civita symbol. So yeah, you see how that works. Okay, we did the scalar triple product just now. Now you can actually guess what remains. What remains is the vector triple product. Okay, consider three vectors A, B, C. Consider this structure: A crossed with B cross C. Again, subscript summation convention is the first thing we will resort to. Crossed with, now this guy I'm going to write directly as BJ CK epsilon JKL EL hat. And then this just becomes AI BJ CK epsilon JKL. This cross product becomes another Levi-Civita ILM and introduce this basis vector EM hat. Now notice the product of two Levi-Civitas. We could use the Levi-Civita identity, but we need the last index to be the same. So we can rearrange the second Levi-Civita symbol to just satisfy the required condition. We can do even permutation to MIL, and notice the L, the last index, is the same. Now we can readily use Levi-Civita identity. We'll have delta JM delta IK minus delta IJ delta MK em hat. Now what we can do is again contract over the indices for each of these cases. So we have ai bm ci minus ai bi cm em hat. So this first guy becomes a dotted with c because they have the same index going on, multiplied with the vector b, because if you take the em hat inside, you'll have bm em hat. So we'll have this minus, well, here we have a dot with b, that's clear, and a c hat. So that is what this vector triple product results in. Yep, it's pretty neat. I personally really like this identity a lot. Now one direct consequence or application of this is in Jacobi's identity. So the setup for this is we have A crossed with B cross C plus C cross A cross B plus B cross C cross A. So I mean, for all the three vector triple products, just apply the formula that we derived over here on top. So for the first guy, you'll have two terms, a dot c b minus a dot b c plus c dot b a minus c dot a b plus b dot a c minus b dot c a. And because of the commutative nature of the dot product, notice the terms that cancel. So c dot b is same as b dot c, so this cancels out with this. Same goes for this and the first term, and this and this term. So all we're left with is 0, and that is Jacobi's identity. This is equal to 0. So yeah, this is pretty neat. I really like it. Okay, let's do another one. A cross B dotted with C cross D let's use a subscript summation directly. I'm skipping the steps of showing the cross in those terms. Dotted with, now introduce some new indices, say A, B and C. Okay, this is a dot product, so we're gonna get a Kronecker delta on top. Just pull out all the scalars first. And the Levi-Civitas as well. We get a Kronecker delta Kc. So I decide to contract over the indices. So I'm changing the C to a K. And lo and behold, we can use the Levi-Civita identity because both these Levi-Civitas have the same last index. So AI, BJ, CA dB, and then delta IA delta JB minus delta IB delta JA. Now AI BJ CI DJ minus AI BJ CJ DI. Note, just group the terms with the same index, A and C, which means we have A dotted with C multiplied with B dotted with D simply minus A dotted with D multiplied by B dotted with C. Since the dot product will result in a scalar, this multiplication makes sense. It's just scalar multiplication. Now, one really nice sort of application of this formula, of the Binet-Cauchy formula. This is the Binet-Cauchy formula. Is Lagrange's identity, which basically says the magnitude of A cross B squared, and we need to find something for this. Well, the magnitude squared is just A crossed with B dotted with itself. And notice this is basically a special case of this guy when C is equal to A and D is equal to B, right? So we can just use this formula down here that we derived. So for the first term we have A dotted with A and then B dotted with B minus A dotted with B times B dotted with A. So this will just be magnitude of A squared magnitude of B squared minus A dotted with B, but the whole thing squared. Now if you were to kind of use the sort of the trigonometric definitions of these guys, you might recall that A cross B, at least the magnitude of this, was magnitude of A times magnitude of B times sine theta, where theta was the angle between them. Similarly, A dotted with B was magnitude of A, magnitude of B, cosine of the angle between them, which was theta. If you plug these things in here, we just have magnitude of A squared, magnitude of B squared, sine squared theta is equal to magnitude of A squared, magnitude of B squared minus this guy here, but squared. So magnitude of A squared, magnitude of B squared, cosine squared theta. And this clearly makes sense because sine squared theta plus cosine squared theta is equal to 1 always. So if you want to make sense of this geometrically in terms of projection onto of parallelogram segments, even the Lagrange's identity makes sense. But I try to do it in a little more general way using the subscript summation convention. Okay, now what if I were to tell you that the vector triple product was just child's play? Let's work with a vector quadruple product. Yes, this is some serious business going on here. So consider A cross B crossed with C cross D. Okay, again, skipping the steps of the cross product inside those brackets. Let's use L here. So well, looks like we're gonna have another Levi-Civita symbol. So epsilon ijk, epsilon lmn, epsilon say kno, eo hat. Well, what we can do is, again, our savior here is the Levi-Civita identity. What we can do is we can try to take the first Levi-Civita and the last Levi-Civita and try to manipulate or do some permutation on the indices of this one. So instead of kno, we'll have okn without a change in sign. ijk, okn or nok. We want the k, right, for the Levi-Civita identity to work. Okay, so now let's do our magic. We will end up with delta ni delta jo minus delta io delta jn, and this epsilon lmn e sub o hat. Okay, we can contract over some indices. We have an here, bo here, cl here, dm, epsilon lmn minus ao bn cldm epsilon lmn, and don't forget the eo hat that's there. Well, do you notice any pattern here? Well, with L, M and N, this kind of looks like a scalar triple product, doesn't it? So we have C crossed with D dotted with A. If you have an I for it, now I wrote this content, so I can't not have an I for this. So we have L, M and N, which match the Levi-Civita. So this is simply C cross D dotted with A and a B vector up front. So let me just square bracket this. Minus, we can do a similar observation here. L, M and N. So we have a B dotted with C cross D and an A vector. This is still only one expansion, one possibility. The other possibility is taking the last two Levi-Civita symbols, not the first and the last, but the last and the second last. So if we do that, we would have had AI, BJ, CL, DM, epsilon IJK, epsilon LMN, epsilon OKN, EO hat. Now again, Levi-Civita identity, because N is a common index. We will have delta LO delta MK minus delta LK delta MO EO hat. AI BJ CO DK epsilon IJK minus AI bj ck do epsilon I j k. We still have the EO hat. Do a similar observation. So we have I think D vector dotted with A cross B, and this scalar triple product is just multiplied by, I believe, C, minus similar observation C dotted with A cross B, and naturally we'll have a D vector up front. So yeah, that is the quadruple vector quadruple product, and it's kind of nice that it extends onto the scalar triple product, because scalar triple products just pop up here. All of these things, they mainly rely on the use of the Levi-Civita identity. Yep. Okay, one thing I want to quickly talk about is vector gradients. So assuming you have a vector field, call it V, and you take the gradient of it. Let's try to write it in terms of the differential operators. So partial with respect to xi, e sub I, and we can also expand V using subscript summation. So Vj Ej hat. Now look at what's going on here. We have two indices here up front. Is there a dot product between them? Is there a cross product between them? Or what's exactly going on? So the right answer to that question is there is a tensor product going on here. It's not a dot product, and it's certainly not a cross product. It's a step above them. So this quantity here, this is a new basis vector. So this guy here, Ej tensored with Ei, is a new basis vector, which means it's pretty much independent of Ei and Ej. Usually when we had vectors, each basis had one vector in it. Now when we are in tensors, we are generalizing vectors. So a basis may not have one vector. A basis may be a tensor basis composed of two simple vectors. And this order matters, by the way. So this is not the same as Ei tensored Ej. Okay, so fine. Even if we have this abstract concept of a tensor, how do we really work with it? Well, this is a rank 2 tensor because each basis has two vectors in it. Vectors are rank 1 tensors. And the scalars are rank 0 tensors, having 0 vectors in their bases. So rank 2 tensors can be represented by, you guessed it, matrices. See, that's why matrix algebra, matrix calculus is extremely useful, because you have them here for tensors and you have them later for group theory as elements of GL3, for example. So yes, this becomes a matrix. So since we have two indices, this will become the indices of the matrix. So this gradient can be, vector gradient can be represented as a matrix. What this means when you're actually computationally calculating it is, well, you have like components for the vector field V. Just take the gradient of each of them. That's what the vector gradient is actually telling you to do. And since you get like you get like a separate, like a 3-element column vector here, and a 3-element column vector here, and a 3-element column vector here. That's why this becomes a matrix, just naturally. The way I think about these new basis vectors that are tensored up is a good analogy I like to give is chemistry. Well, you have atoms. Say you have hydrogen and oxygen, and you can combine them to form water. Now, hydrogen is a non-supporter of combustion. If you light something in hydrogen, it will extinguish it out. Oxygen, however, is a supporter of combustion. It kind of rekindles a glowing splinter. Water, on the other hand, is used to put out fires. Hydrogen is indifferent towards fire. Oxygen supports fire. Water is used to put out fire. So there's a clear contradiction of properties, like the properties of water do not depend on hydrogen and oxygen, its constituent elements. So think about a tensor product that way, a tensor basis that way. So say EI is your hydrogen, EJ is your oxygen. This quantity, this tensored up basis, is water. So it has independent properties than those of its constituent basis vectors. I hope that clears things up for you. You can also have, since you have vector gradients, you can have vector Laplacians, and the idea is pretty much the same. Take a vector gradient and take the divergence of that. So which is basically like saying, take the scalar Laplacian of each of the components of V. That's what this is actually telling you to do. And this is extremely useful in electrodynamics, especially when you're dealing with like magnetic fields. You get a vector Laplace's equation, not a simple Laplace equation. You get a vector Laplace's equation for the magnetic field at least. So I hope this video was enjoyable. I hope you learned a lot. This was pretty short, but yeah, it was. I ensured my content wasn't that boring. Please like and subscribe to my channel, guys. Recommend me to your friends. Stay tuned for more content, and in the meantime, just peace out.